So, last class I have discussed that how you can determine the bearing capacity for inclined load, and I have used the Meyerhof bearing capacity equation. But today or this class I will discuss that how you can calculate the bearing capacity if you use Henson equation under inclined load. So, if the foundation is under inclined load, then either HB or HL. So, what does it mean? That HB means horizontal component of the inclined load is parallel to B, and HL means the horizontal component of the inclined load is parallel to length. Okay. So, sometimes in previous problem I have given inclined load itself, but sometimes the vertical load and the horizontal load can be given separately. That means, the footing is under vertical load as well as the horizontal load. So, you can get the resultant inclined load, and then you can determine the or find the inclination with respect to vertical, and you can solve it like the previous problem. But that means two way, either the inclined load can be given directly, then you have to determine the horizontal and vertical component of that load, and another option that vertical and horizontal component can be given separately. In such case, you can get the resultant load, inclined load also, and the amount of inclination also. So, but as I mentioned, if I want to use the Henson theory under inclined load, then only inclination is not sufficient. We have to know that the vertical or the horizontal component of the load is acting in which direction, whether it is a parallel to L or parallel to B, or in both the direction horizontal load is acting. That is also one option, that in the both the direction horizontal load can act along with the vertical load. So, in such case we can use the Henson theory and the basic theory. But the basic theory is straightforward, not much modifications are required, but the Henson theory we have to do few modifications, okay, as we proposed in previous lectures. So, we have already proposed, or I have already discussed about the Henson theory in previous lectures, but those you can use if loading is perfectly vertical, but if the loading is inclined, then you have to do few modifications. So, what are those modifications? So, first note that with a vertical load and a horizontal load HL, that is HL greater than 0, I mean HL means horizontal load parallel to length, and either HB equal to 0 or HB greater than 1, HB means horizontal load parallel to width. Then we have to calculate two sets of shape factors and inclination factors and the depth factors. What does it mean? That suppose if this is your say foundation, okay, this is your foundation, and you have a vertical load and you have a horizontal load, and horizontal load is HL. For example, this is the say width of the foundation, and this is a length of the foundation. Okay. So, now if the horizontal load is parallel to HL, because your horizontal load is acting. So, I should then draw, this is actually the perpendicular to the plane. So, this should be a dot, or which is perpendicular to the plane, this horizontal load. So, that means this is HL, or your HB can be 0 or HB greater than 0. So, that means, if your horizontal component of the inclined load or the horizontal load is parallel to L, in such case we have to consider two sets of shape factor, depth factor, inclination factor to incorporate the inclined load effect in these factors or in bearing capacity equations. So, and in such case, when you use these two sets, we have to interchange the L and B also, and if the eccentric loading is there, then L dash and B dash. But this we have to, these two sets we have to calculate only if L is present along, or if HB can be 0 or HL is there along with HB also. But if the HL is 0 and you have only HB, then one set is sufficient, and that is your normal set that I have discussed in the previous lectures. That means, this equation number 1. So, that we have to use only that if HL is equal to 0, then only one set is sufficient. That means, if HL is equal to 0, then you calculate the shape factor, depth factor, inclination factor, and your all this factor as usual as you do, then that is sufficient. But if HL is not 0, then we have to use equation 1 and 2, equation 1 and equation 2 both if HL is not equal to 0. That means, HL is there. There can be HB can be 0 or there can be HB also. So, that means, here HL is equal to 0 and HB is not equal to 0. That means, this is the one case. Another case, both HL we have to use equation 1 and 2 if HL is not equal to 0, but there can be HB can be 0 or HB can be not equal to 0 also. So, that means, the three cases, one case that HL equal to 0, HB equal to not equal to 0, then only the equation 1 or the one set is sufficient. But if HL is not equal to 0, HB equal to 0, then two sets. Again, if HL not equal to 0, HB not equal to 0, again two sets. That means, whenever HL is not equal to 0, whether HB present or not, then we have to take two sets of factors, and you have to calculate the bearing capacity by using these two equations. So, what is the difference between two equations? As I mentioned, you have to interchange the L and B. So, that means, in first equation the factors we have to calculate the normal way as we do for the considering, that is the B, all are in terms of B. That means, the B by L, dF by B, the way it is given, and we have to use in the third term B. If it is eccentric loading, then you have to go for B dash. So, but if we have to go for both the sets, then one set with terms of B, another set with terms of L, and we have, that means, L means we have to interchange B by L and L by B. That means, now it is not B by L, it will be L by B or dF by L, and in the third term we have to use the L, not the B. And the lowest of these two will give us the bearing capacity. Clear? Because clear these things, because this is important, because for Henson theory. Mere of this type of requirement is not there, even not in IS code also, even not in basic also, because basic as you remember that in inclination factor calculation, already that the direction of load, whether parallel to H or parallel to L or parallel to B, is already incorporated. So, in basic also it is not required. So, but in Henson it is required. So, this is one modification we have to do. Another modification, so that means this is the factors I am talking about. So, now when you calculate the SCB, because there is a SCB, so that means SCB, then you use B. Now, if you calculate SCL, then SCB means this equation. If you use the SCL, then you have to use 1 plus NQ NC L by B, okay, for SCL. Similarly, for dF by B also you have to replace by dF by L in calculation of DCL, okay, or DQL, like this. And then the these factors are again you have to calculate, because this is effective area whether A or B does not matter, it is area. Again these other things are same as I discussed, and for eccentric loading you remember where you have to use L dash and B dash, where you have to use L and B. Okay. Now, the second modification, that to incorporate this inclination effect, that for Henson theory it is suggested to inclination factor to compute the shape factor as follows, that if the load is inclined. So, Henson bearing capacity equation, when you calculate the shape factor, then you modify the shape factor, because original shape factor what is given? The shape factor is given that SC NQ divided by B by L. Okay. So, now that we have to use by multiply ICB. That means, first you have to calculate these inclination factors, then that inclination factor we have to multiply with these respective terms in shape factor. Okay. So, initially shape factor, if you see this table, that so that means this table you can use if loading is perfectly vertical. You cannot use this table to calculate the shape factor if loading is inclined or there is a horizontal load is present, okay, as per Henson. In such case, we have to modify that. First, we have to calculate the inclination factors, then we have to modify these equations, because you can see that if it is SCB, this ICB you have to multiply with B. If it is SCL, then this will be L, this will be B, then we have to multiply with ICL. ICL means actually this is your ICL means whether your horizontal load is in there is a HL or HB, that you have to consider. If it is the HL, then you have to consider HL when calculate the ICL. If this is ICB, then you consider HB. If HB is equal to 0, then the ICB will be just 0.5. Clear? So, now ICL means this will be, so for example, I can write that for that for say IQB. So, that means this will be your HB, HB. Okay? And if it is IQL, then it is be L. That means the horizontal load parallel to L. Now, sometimes the HB can be 0, HL can be 0 also. So, in such case you put 0 and calculate the HQ and HL, all these things. But this, as I mentioned, these HB, L and B, that part you have to use only if HL is not equal to 0. So, that means there is the option when you the HL cannot be 0 when you calculate QL or QB. Only option is that HB has to be 0, can be 0, not has to be 0. It can be 0, may not be 0 also. Okay, it may be 0, may not be 0, but HL will always be there. Then only I have to go these 2 sets. Otherwise, only one set is sufficient. Is HL is 0, then only one set is sufficient. If HL is not equal to 0, then only you have to go for 2 sets, that is IQP or IQL. In that case, HB may be 0, may not be 0. Okay. So, this is the case, we have to modify that. That means, we have to interchange this L, that means, this is B, ICB, and similarly LB, and then for S gamma B, this is B by L, I gamma B, I L B, I gamma L, and this is also interchange that L I gamma L, B I gamma B, and these things are, you have to modify the shape factors, and again these 2 bearing capacity equation you have to use, and lowest of these 2 will give us the bearing capacity value, and this note is also given. And one more thing that I want to mention, that suppose if your HL is 0, but only HB is present, then also you have to do this modification. Okay. So, that means you have to calculate the inclination factor, and then you have to multiply with this inclination factor with the shape factors. But in such case, this B, SCB or SCL, these 2 sets are not required. We have to go for only one set, that is SCB, but this modification is must. If that means, if the loading is inclined or the horizontal load is parallel to H or L or B, but this modification to calculate the shape factor you have to do, but if HL is not equal to 0, then we have to go for 2 sets, and if HL is equal to 0, then you have to go for one set. Okay. So, now this is Henson as per basic you can see, but remember that these modifications you have to go only with shape factor, not with depth factor. Okay, with shape factor only, not with depth factor. So, and for basic, this is the basic table, here no such modifications are required. The only one way you have to do it, whether it is parallel to L or parallel to B, and because that parallel to L or parallel to B effect is already incorporated to calculate the inclination factor. So, no such modifications are required in case of basic. So, you can do as it is, but for the Henson these modifications are suggested. So, now let us do one particular problem, and then I can more clearly explain that how these modification can be incorporated in Henson's equation. So, the problem is that this is the footing, okay. So, this is in length direction. So, this is the length of the footing is equal to 3 meter. So, there is a vertical component of the load which is 1000 kilonewton, and there is a horizontal component of the load HL which is say 300 kilonewton, okay, and which is parallel to L, because this is the L direction. So, that means, this is if I go for this plan of the footing. So, this is the length direction L which is 3 meter, and this is the width direction B which is 2 meter. So, the your horizontal load which is parallel to L and parallel to B, HB is given equal to 0. So, that means, no parallel component of load is no component of load parallel to B is acting. but does not matter, as HL is not equal to 0, then you have to go for 2 sets of equation as per the Henson, because we are using the Henson's bearing capacity as per the equation. But in such case, as I mentioned, HB can be may be 0, may not be 0. This case HB is 0, but there is a option, there is a case that where both HL and HB are present. So, so that means this is the case, and then my soil property, unit weight of the soil is 19 kilonewton per meter cube. Phi value is equal to 40 degree, C value is equal to 0, water table is not considered. Okay. And before we solve this question, one more thing I want to mention, that that this is a your rectangular footing. Okay. So, now if sometimes you will find that we will test the soil sample in triaxial, okay, and then we will get a phi value, and that I want to use. So, that phi value we can use for this case, but or if my loading is steep footing, but I cannot use directly that phi value for steep footing condition, because steep footing is a plane strain condition, and when you calculate determine the triaxial phi, that is not under plane strain condition. Okay. So, now if you have a triaxial phi value is given, and if you want to use them under plane strain condition or plane strain condition, or in other words where the length of foundation is higher than the width of the foundation, then we have to modify the phi value. So, in your case, if directly phi is given, then you can use that phi, either it is a steep footing or the rectangular footing or square footing. But if in the question it is given phi triaxial, then you check whether that phi value you can directly use, or you have to do some modification to use it for the steep footing case, or when the length of the foundation is much higher than the width of the foundation. Clear? So, that I am giving, suppose if your phi triaxial is given, which is called phi TR. Now, if your L by B, or if it is eccentric loading L dash by B dash is greater than 2, then you use phi plane strain or modified phi, which is 1.5 times phi triaxial minus 17 degree. Okay. So, that means if length is 2 times more than the width, then if phi triaxial is given, then you convert it by using this equation. Now, if your L by B or L dash by B dash is less than equal to 2, then you use phi triaxial. Now, if any case that phi triaxial is less than equal to 34 degree, then you use, whether it is length is 2 times more than the width, you use phi triaxial is equal to phi plane strain. Okay. So, that means, if it is greater than 34 degree and if length is 2 times more than the width, then you convert the phi triaxial with this equation. If it is less than 34 degree or equal to 34 degree, then whatever the case, use that 34 degree, and if length is less than equal to 2 times the width, and but phi is more than 34, phi triaxial is more than 34 degree, then you use that phi triaxial. Okay. So, so but if only phi is given for such case, for this problem only phi is given, because it is specifically not mentioned that how this phi is been determined, then you use whatever the condition, whatever the length or b ratio, use the phi is equal to 40, whatever the phi is given. Okay. So, and then for one more condition, as I mentioned in the previous problem, I have given the inclined load directly and the inclination. But in this problem, as the basic need to know that basic equation needs to know that whether the loading is horizontal load is parallel to H or B. So, it is given like this. You can convert it to inclined load also by using this equation, or just take the resultant, that is V square plus H here HL square, which is equal to 1000 square plus 300 square. So, this is equal to 1044 kilonewton, and the angle now you know that V is equal to R cos I or alpha. So, that I is equal to cos inverse V by R. So, which is equal to 16.7 degree here. So, the angle with vertical is also can be known is 16.7, and the resultant load is or inclined load is 1044 kilonewton. But as we are using the Henson's equation, so we will use this way. Okay. So, now we have to calculate the two sets of the bearing capacity factors, because your HL is not equal to 0. As HL is not equal to 0, then we have to go for two sets of bearing capacity or the correction factors. And so, as for depth correction factors, no modifications are suggested as per Henson theory. So, first we will calculate the depth factors. So, that but depth factors also we have to go for two sets, but only that modification to incorporate the inclination factor is suggested only with shape factor, not with depth factor. But depth factor also we have to go for two sets if HL is not equal to 0. So, now my dq B is equal to, why I am not going for DC, because as C equal to 0. So, first term I am not calculating. So, that is equal to 1 plus 2 tan phi as per Henson, 1 minus sin phi to the power square df by B. Okay. So, that is 1 plus 2 tan 40 degree, 1 minus sin 40 degree to this power square into df is 1 meter, B is 2 meter. So, this is 1.107. Okay. Now, I will go for dql. So, that is 1 plus 2 tan phi 1 minus sin phi square, that is df by L, because this is dql. Now, this is equal to 1 plus 2 tan 40 degree 1 minus sin 40 degree square, df is 1, L is 3 meter. So, that value is 1.071, and as per the Henson, the d gamma B and d gamma L all both are 1. Okay. So, now I have to go for IQ B and the IQ gamma. IQ B, IQ L, I gamma B, I gamma L. First, we have to calculate the inclination factor, then you have to modify the shape factor, and then we have to use them. So, in the next class I will solve the remaining part of this problem, because I have determined the depth factors only, because where only you have to go for two sets as H L equal to 0, but that modification you have to go to the shape factors. So, that I will do in the next class. Thank you.